Okay, it's time to revisit the end of Chapter 2 and talk a little bit more about properties of matrices and matrix arithmetic. By now, we should already know that multiplication is not commutative in linear algebra. What that means is that A times B is not the same as B times A. Order of multiplication matters in a big way. Oftentimes, this will be defined, and this multiplication won't even be defined. However, matrix multiplication does satisfy the distributive and associative properties. So hopefully you remember these properties from regular algebra. Here we see the distributive property. So here I have a matrix on the left outside of the parentheses. And what this means is that I can distribute this multiplication into both terms inside the parentheses. And I can do the same thing with multiplication on the right. Okay, so B plus C, that quantity times A is B times A plus C times A. We also have the associative property when we talk about multiplication and addition. Here we're just talking about multiplication. So if I have a matrix product, A times B times C, it doesn't matter what order I compute this in as long as I respect the order that's written. So I can first compute B times C and then multiply that on the on the left by A. So I have to respect the order as it's written, but I can reorder the parentheses. So let's use those properties just to simplify some linear algebra expressions. Here I have a matrix, and I'm multiplying it by this quantity in parentheses, lambda would be a scalar, remember, times the identity matrix, plus A inverse times some other matrix C. Okay, so the first thing we can do is use the distributive property. So I distribute the A inside to both terms in the parentheses. And now what I want to realize is that scalar multiplication is commutative, right? Anytime I multiply by a scalar, I can do it on the left or the right side. So I want to move this scalar. Always we want to put scalars on the left side of matrices. It's just something that we prefer to do. And so if I were to do that, I would have lambda times A times I, the identity matrix. And so anything times the identity matrix is just what we started with. So A times I is A. And then over here, I can use the associative property and realize that rather than first multiply A inverse times C, I'll first multiply A times A inverse. And that will give me the identity matrix multiplied by C is just C. So this is a simplified version of this same expression. Now, in addition to just talking about matrix multiplication, there's also some properties of the transpose operation that we should be familiar with going forward. The first is that the transpose respects addition. And what that means is that if I want to take the transpose of a sum, well, that's actually going to be the sum of each matrix transposed. Okay, so you almost can think about this as the notation being distributed into the parentheses. Okay, so the transpose of a sum is the sum of the transpose. The next one's a little strange. So the transpose of a product, to compute that, we reverse the order of the individual terms in that product. Okay, so AB, that quantity transposed, is B transpose times A transpose. So again, I reverse the order of the factors here. And that will be true not just for two factors in a product, but for as many as I have. So if I have A times B times C times D transposed, well, to compute that, I would reverse the order of everything inside these parentheses. So I have D transpose, C transpose, B transpose, A transpose. Okay, so this is a very important property. Also, the inverse of a matrix transpose is simply the transpose of the inverse. So sometimes people will use shorthand notation, and I'll probably follow this convention most of the time, and just write A to the minus T. So it's the transpose of the inverse. Transpose of the inverse and the inverse of the transpose are the same thing. And then these last two should be pretty straightforward. If I have a scalar multiple of a matrix and I take the transpose of that, it's the same as taking the scalar multiple of the transposed matrix. Another way you can say this is that the transpose of a scalar is just that same scalar. And we've also already seen the fact that if I take the transpose of a transpose, I get back to the original matrix. So let's see how we can put these to use. These first three will be the ones that come in handy the most, I think, throughout our course. So let's start with some matrices, and let's determine whether or not they're symmetric. So you'll remember that a matrix is symmetric as long as the matrix is equal to its transpose. So that's what we want to ask ourselves. Is the transpose equal to the original matrix? So let's take this whole matrix, X transpose X, and take the transpose of it. Well, to do that, I want to use the reverse order law. So what I'm going to get is X transpose, which is written here, times X transpose transpose. X transpose transpose. Okay, and then, again, when I do a double transpose, I just get back to the original X. So when I finally simplify this, I get back to X transpose X, which is what I started with. So yes, that matrix is symmetric. Here's another one. The identity matrix plus some vector times X transpose. Some vector X times itself transpose. Okay, so remember, this is called an outer product. This is a column vector times a row vector, and that makes a rank 1 matrix. So again, we ask ourselves, is the transpose equal to the original? So we take the transpose of this entire sum here, and we'll see we have I transpose plus this term here, transpose. So again, I use the reverse order law when I get to this second term in the sum, which will give me X transpose transpose, which is just X, and then X transpose. So I do, in fact, get back to the original. This is an example of a symmetric matrix. The identity matrix transpose is still the identity matrix. I hope you can all agree with that. In fact, all diagonal matrices, when I take the transpose of them, I get back to the original because they're symmetric. Okay, so now let's suppose I have A, and that's symmetric. So that means I know A equals A transpose. I also have B, and that's symmetric. B equals B transpose. What about the product? What if I multiply these two symmetric matrices together, A times B? Well, let's check. Let's look at the product and take the transpose. Well, the reverse order law says that's B transpose A transpose. Now I know already that these are symmetric, right? So B transpose, well, that's just B. A transpose, that's just A. So what I get is BA. That's not the same thing as AB, right? Because matrix multiplication is not commutative. So the answer here is no, not in general. There may be some very special cases. For example, if one of these is the identity matrix, that would work. But in general, no, the product of symmetric matrices is not symmetric. Okay, let's also look at simplifying expressions. So here I have an algebraic expression, and I want to simplify it using the properties. So the first thing we'll do is start with this transpose here and use the reverse order law. So that will give me B transpose and then A transpose transpose. So B transpose, A transpose transpose. And then this A inverse is still here. Okay, well, the A transpose transpose, that's just A. And now I have A times A inverse, which is the identity matrix. So I just end up with B transpose here. So now here's a good spot for you to check your understanding and practice your matrix arithmetic. And if you did this properly, this is the solution you should have come up with. For this first expression, you can see the reverse order law is going to move this C transpose. It's going to make it a C and move it to this side of the product. And then multiplying it by C inverse, that will go away. And so I have just the transpose of the A plus B left. Here, when I take the transpose of X transpose X, well, it turns out that's symmetric. So what returns is just X transpose X. X transpose X is a matrix. I'm multiplying it by its inverse. And so what I'm left with is the identity. And then you should easily be able to show that all three of these expressions are, in fact, symmetric. So the last thing I just want to mention briefly is matrix powers. So if we compute the powers of a matrix, we do this is defined in the same way it is for scalars. If I raise something to the 0th power, I get the identity matrix. So you'll remember that a scalar to the 0th power is 1. The identity matrix is like 1 for matrices. Okay, so the first power is just A. The second power is A times A. The third power is A times A times A. I think you get the picture. So the time that we have to be a little careful with this is if we're going to power a product of matrices. Okay, so if I have AB squared, that means that I have AB times AB, which is equal to AB, AB. Okay, so it's not equal to A squared times B squared, like you would see for scalar algebra. Okay, and that brings us to the end of today's topic.